title of the talk is Wonderful World of Polymers. All of you know about polymers. We are in the age of polymers. We started with Stone Age and now we are in the polymer age. Any doubts about it? See, we sit and stand on them. We hold handles, turn knobs, drink tea or coffee, eat from the articles made out of these polymers. We travel in vehicles, we fly on aeroplanes that are increasingly using these materials. And these are the man-made materials, what we call polymers. Sorry, I have to wear specs. So you have studied what are polymers. Large molecules. The giant molecules. Poly means many, mer means parts. Many parts put together to make a giant molecule. Sodium chloride crystal has Na plus Cl minus. Can I call it a polymer? If you take the crystal from one end, sodium chloride is there, linked together. Why it is not a polymer? Ethylene gives you polyethylene. Sodium chloride. Why it is not a polymer? One loud answer. Inorganic polymers, sir. Their silicones are inorganic polymers. Yeah, why don't you call them polymers? Polymers also, ultimately, if you have different polymers of different molecular weights, number of monomer units will be different. What is important is how they are linked together. The mers, the units are joined together by a bond. What is that bond? Covalent bond. So when we say polymers, the monomer units are linked together, large number of monomer units linked together by means of a covalent bond. If you don't mention that, whatever large collection of molecules you have will not end up in a polymer. That is the polymer. Exactly this. A pearl, a mer, many pearls together, and then put them through a string which acts, it's a bond actually, linking all of them to give a necklace. You have a polymer there. Similarly, at the bottom we have shown a small molecule, isoprene. It gives us polyisoprene. All these small molecules are linked together to give a large molecule. Exactly this way we have a necklace. If I break it, if I break the string, I depolymerize it. I polymerize it to give a large molecule. I depolymerize it to give individual molecules. You break the necklace, the pearls will be scattered all over. That's what we can do. Why these are interesting? Why these molecules are interesting? I told you the use. They are slowly replacing conventional materials, and ultimately they will be replacing almost everything, including our body parts. If there is a broken bone or a joint, it will be a polymer material that will be substituting it. If you look through the development, polymer is the general name that is given. We sometimes say plastic bag, they don't know. Plastic. You have rubbers, the rubber tire, ubiquitous everywhere. Fibers, polyester shirts, adhesives, Fevicol, Quick Fix, and then surface coating, paints, You see all the heroes of the film industry painting their walls. So these are the different types of polymers that we come across. Their applications, their technologies are developed separately. Technology developed adhesives without knowing that the neighboring industry, the paints, has similar chemistry behind it. When we say giant molecules, how big? Comparison is done. Small molecule, glucose. You see the molecular weight, 180. Formula C6H12O6. And a big molecule, hemoglobin, was shown by Dr. Jadeja. He had shown only part of it. If you have to write the molecular formula of it, you can see CHNSFE. What is the molecular weight? And this is one of the smaller molecules, the polymers. See the last line. A polymer, a protein, naturally occurring polymer, which has a molecular weight of 2,993,000. So that's why we say these are giant molecules, macromolecules. Why they are interesting? They are interesting because they show unusual properties. The properties, the smaller molecules from which they are made, is totally different. I'll give you 3 or 4 examples. As children, you might have played in the bathroom. The bucket is full of water. When the mother is not there, first thing that you do would be put your hand and swirl it. Looking at that water swirling, producing a vortex. The lowest point of water will be at the middle, where your hand is. You have seen that. That is the normal phenomena that we see. But if you have a polymer melt or a polymer solution and you put a stirrer, hand you cannot put naturally, you put a stirrer and put on the switch, and you expect the polymer solution to behave the way water behaves. Exactly the reverse happens. Instead of going down like this, it starts rising on the stirrer rod. It goes up. Different. Why polymers are interesting? Polymers are interesting because they do not behave the way we expect them to behave. The second one, you see the ball on this side. You play the crazy ball, a ball made up of a special type of polymer. You bounce it, you can play with it. After some time, when you are tired of playing, you put it on the table. It flattens, starts flowing, and as a liquid, it will come and fall to the ground. It was behaving like a solid, rubbery solid, and the other, after some time, you see it flowing like a liquid. No other material will do that. It shows both the properties, fluidity as well as rigidity. The third example, it's at a flattened portion I have shown, the silly-putty. The pendulums, generally you put a string and suspend a weight to it. You have a metal wire, suspend a weight and heat it. What do you expect? The wire, it expands, it lengthens it. It becomes longer. You try the same experiment with the string made up of polymer, suspend the weight, heat it, taking care not to burn it because polymers are inflammable. You increase the temperature. Instead of lengthening, it shortens. Exactly contrary to our experience. So why polymers are interesting? Because they behave differently. Why they behave differently and show so many interesting properties. I have given you only 3 examples. A 4th example I can think of. rubber tube, the flexible rubber tube that you have, you can bend it the way you want it. In the laboratory I've used it for passing water through the condenser. The same rubber tube, you dip it in liquid nitrogen where the temperature is low, take it out and bang it to the table. It shatters like glass. The rubber tube, which was flexible and you could play with it, behaves like a glass at that temperature, and you go and try to pick it up, it's again rubbery. By the time you go and try to pick that piece of rubber, which was like glassy, it has become soft again, rubbery. At one temperature it behaves like glass, at another temperature it behaves flexible like rubbery material. The unusual property. And all these properties can ultimately be linked with one property of the polymer. What is it? All the interesting properties ultimately lead to us only one point. Large molecular weight. All these properties ultimately be due to the large molecular weight that polymers have. If their molecular weight is low, they do not possess this property. As the molecular weight becomes higher, and higher, when crosses a particular value, it starts getting those properties. See, nature has provided everything, like the fragrance and the flavors which Dr. Jadeja showed. Nature has given us other things in the form of polymers. All those listed: cotton, silk, hair, wood, protein, shellac, rubber, horns, and even tortoise shells are all polymers of different types, and we have used them for clothing ourselves, as shelter, as food, whatever. We have exploited nature to start with for our basic needs like food, clothing, and shelter. And nature has provided different types of polymers to us. Then we started with the horn. If you want to make the comb, it was the horn of the animals which was used. So similarly, people started using the naturally occurring polymers for our daily needs.